These are the notes for chapter 3, and we're going to take a look at um, starting this part. We're just going to look at the chapter 3 part with the vectors, and then in class we'll take a look at the two-dimensional kinematics. And so the first thing about vectors is how to add them. And again, a vector is just an arrow. And so if I have two vectors here, A and B, to add B to A, what you have to do is you have to draw them tip to tail. Doesn't matter what order. But for example, this here is the tip of A, this is the tail of B, so they would have to move together, as is shown here. And then the resultant is always going to start from where you started and goes to the end. So it's kind of like thinking about displacement. It's your starting place to your ending place, and it's the as the crow flies. And this is often called, this A plus B here is often called the resultant vector. And it can be anything that's a vector. So we've talked about displacement as a vector, velocity as a vector, acceleration as a vector. And so all of these things can be added in this way. But the big thing, the key is that they have to be drawn tip to tail. If you want to subtract these vectors, it's basically adding, because A plus B is the same as A minus a negative B. And so what we're going to do is we're going to find what negative B is. In other words, we just flip it around. So if you look, this is what negative B will look like, because it's just opposite. It's the same length as B, but it's just pointing in the opposite direction. And so now I'm going to take A and add this negative B and draw those two tip to tail. And then the resultant again will be from where we start to where we end here. And that would be the resultant vector of A minus B. So that's really the biggest thing about drawing vectors. They have to be drawn tip to tail. It's probably the biggest thing. So an example of why we might subtract vectors, remember that the acceleration is the final velocity minus the original velocity. And so that would be a case where if you had two vectors representing the two velocities, final and original, you would have to flip the original velocity around. You'd have to find that would be, in a sense, this minus b. Okay, so most of the time when we solve vector problems, though, we're going to be using trig, basic sine, cosine, and tangent stuff. So if, for example, I have this particular vector right here, where I have, it's just a line, it's called r because it's the resultant at some particular angle. You would probably agree that this particular vector is pointing up and it's pointing to the right, or it's pointing north and it's pointing east, it's pointing both. So we can split it into vertical, sometimes known as y, and horizontal components just using basic trig. So if we were to sketch it, this would be the piece here that is pointing to the right of that particular vector. And this would be the piece that's pointing up for that particular vector. Notice that we have made a right triangle out of this. And so that's where now we can use SOHCAHTOA, sine, cosine, and tangent, to solve this particular triangle. So the x component, if I look, it is adjacent to the angle, and cosine always deals with adjacent and the hypotenuse. And so that's why you end up with r times the cosine of the angle. And then the y component here is the opposite of the angle, and that involves the sine. Sine is opposite over hypotenuse, and that's why you get r sine of the angle. This is true for this particular case. You do have to be a little bit careful when we go on inclines. Sometimes these seem to flip, but it always comes back to where the angle is in the triangle. If it's the adjacent side, you're going to be doing cosine to find the component, and if it's opposite, you're going to be using sine to find the component. And once, to kind of go backwards, if we know components, we can use the Pythagorean theorem to find the value for r. right? If we know two sides of a right triangle, we can find the third using Pythagorean theorem. All right, so we have a couple of examples here. So we have a car traveling 250 kilometers in a direction of 150 degrees. How far did the car travel west and north? And so I'm going to come down here and find a pen. So this vector is pointing kind of this way at, and it's a value of 250 km. And so what I want to find, if I change my pen color here, I want to find the piece that points this way. That's going to be the piece that points west. And I want to find the piece in green that points up. That would be the north piece. And so to do that, again, I'm going to use the components. I'm going to use the 150 degrees that I'm given in the problem. You probably recognize that the angle inside the triangle is 30 degrees. I'm going to use 150, and I'm going to show you why here in a moment. So if I change my pen color here to black, and so this west component here is going to be just 250 times the cosine of 150. And when I plug that number in, I get 16.5 kilometers, and it's negative. And that's the advantage of using this 150 degrees. If I plug in 250 cosine of 30 degrees, I'm going to get just a positive 216. Technically, this piece, this component, points to the left. That's a negative direction, and so I should have a negative value. If I do this north side, it's just going to be 250 times the sine of 150, and if you do the sine of 30, it's going to come out the same numerical answer. I get 125 kilometers. And so those are the values for this object pointing, those are the components of that original vector. Okay, let's take that off. I don't want the pen anymore. Arrow. Okay. So what do we do if we don't have a right triangle? Well, if we don't have a right triangle, essentially we need to make it a right triangle. So what we do is we first find the x components of all the vectors and we add them up to get r, what we call rx, kind of the total of all the x's. Do the same for the y's. So find the y components of all the vectors, add them together to get ry. And then we will use these two components to find the value for r using the Pythagorean theorem, because again what we're doing is creating a right triangle. And then we can find the angle in the triangle by doing the inverse tangent of ry over rx. And then we can use that angle inside the triangle to figure out the direction of the resultant r from a sketch that we've made. And so now I want to do an example of this type of problem. So here we have a dog named Chuckles goes for a walk in the neighborhood. He walks 150 meters at 20 degrees, then walks 200 meters at 160 degrees while chasing a squirrel. And we want to find his displacement from home. So initially, we're going to have, oh, and I want to go backwards. So previous. All right, so here we are. And go to the example slide. Okay, so here we are at Chuckles, and so here I have drawn a triangle of his motion. So he first walks this way, here, 20 degrees, 150 meters, and then he walks 200 meters at 160 degrees. And so you can clearly see that's not a right triangle. And if I were to change my pen color here to even just a green. The resultant is going to be this. So this is his Chuckles displacement. I need to figure out how big that is, and I need to figure out the angles. So this, again, is not a right triangle. So what I need to do is I need to find the x components. And the x components, I'm just going to have 150 cosine of 20. And I'm going to have 200 cosine of 160. And I need to find these values, and if I add them up, I get what's called Rx. And so when I do those calculations, I get 141 for that first component, and I get a negative 188. And if I add them together, that's a negative 47, which means that that x component points to the left. And if you look at that green vector up there, it does point to the left. So now if I change and do the y components, I need to do the same thing for the y components. The only difference is that the cosine has now changed to sine. So I have 150 sine of 20 and 200 sine of 160. And if I add these, find these and add them together, that's going to give me Ry. And so if I found 150 sine of 20 as 51.3, and the 200 sine of 160 is 68.4, and if I add those together, I get 119.7. And so now I can find R, because R is just the square root of 47 squared. And I'm not going to put the negative in there because that should cancel. 119.7 squared. And if I do all of that, I end up with 128.6 meters is how far away he is as the crow flies. So now the other piece I need is direction. So remember we said to find the angle. And the angle I'm finding here is this one, because essentially what I have done is I have found this is Rx in the blue here, and this is Ry. Sorry, that's not straight, but I'm looking at this angle then inside that triangle. Is the inverse tangent of 119.7 divided by 47. And this comes out to be 68.6. Now remember, there was another step. This right here is not the direction this vector points. You can see it clearly points past 90 degrees. But if I look, this is 180 right here. So if I subtract that 68.6 from 180, that should give me the actual direction of the vector. So 180 minus 68.6 is 111.4 degrees. So there is the direction of the vector. So it's really just all about finding those components and then making a right triangle out of your resultant is what we've done. And that concludes these notes. We'll see you in class.